Okay, so we're going live now. Let me get me up there. All right. So this is the summary of last class, which is basically our checklist for what we're trying to get through today. So it's a little different than maybe your high school oh, sorry. I forget. Every time I hit go live, it starts streaming on the other screen here, and then I get distracted. I'm like, oh crap. Sorry about that. I hear myself talking and I'm horrified. So, okay, our goal today is to discuss this stuff. All right. And we're talking about acceleration, velocity, and notice vectors are implied on these equations, but not drawn. And we want to talk about instantaneous acceleration and instantaneous velocity. And maybe you've seen some other equations. We want to talk about these ones. In particular, we see that if you have position, velocity, and acceleration, you take derivatives to go this way, and you do integrals to go this way. And you might be wondering, this might look slightly different than your calculus class. I'll explain those differences today. But the short version is you take a derivative of position to get the velocity, you take a derivative of velocity to get acceleration, and you integrate to go the other way. Seems really easy. Seems like something you've done in calc class, but physics is a little bit different. There are some idiosyncrasies and some details that are just you got to pay attention to. We'll discuss those today. Finally, at the end of after we do this for about an hour and maybe 15 minutes or so, or an hour, then we're going to go over into graphing these things. And so obviously derivatives relate to slopes and integrals relate to areas. And so we want to get basically the details of how calculus relates to all this stuff and how that calculus relates to the graphs and get a strong conceptual understanding. Now, before we go ahead, let's think big picture here for a second. Do these graphs mean that much to you? Probably not. But the process of learning how to read graphs carefully, paying attention to things like units and what they mean. What is the units of a slope? What are the units of an area? Best practices for thinking about those things and how to go about them. That is kind of what matters. I call that big concept graphical literacy, right? If you're going to communicate as a scientist, you need to be literate in the speak of graphs, so to speak. So you need to be able to talk graphs. All right. So we're going to try and get you there, or at least most of the way there in class today. Um, so, uh, and then since that's review, we'll probably come back to that later. You can, again, check out the live stream later. I want to point out the pieces of chapter 2 that we're going to discuss and where these fit in. Okay. So we are going to have several different pieces. There's calculus with X, V, and A. That's one piece. There's plotting or graphs, however you want to say it. And the last one is going to be word problems on specific on constant acceleration kinematics. So, and all of these together, you got 1, 2, 3. These are the three pieces. All of this together adds up to 1D motion, or sometimes it's called 1D kinematics. All right. Again, the particular physics of this stuff is not necessarily the most exciting or riveting or maybe even meaningful. However, what is important is the process that we have to go through to learn these things will make you better at learning technical content that really does matter to you. And to be honest, this will be used intermittently throughout the rest of your physics and engineering career. So this stuff will show up a lot. So we'll get the basics down so that you have a baseline for those other classes. Any questions before we get into problems? Let me get the gallery view. All right, let's rock it. So let me go back to speaker view, get a screen share. Let's see if I got this right. All right. So, whoops, get this here. Whoa, what is this thing? Let's get this out of here. Sorry about that. And then just so we're starting, I'm going to start this a little bit differently than I did in Physics 110, or maybe that you did in high school physics. I don't know. So I'm on page 42. All right. And I'm looking at this stuff up at the top. All right. And so I think a lot of you will understand this, but notice this extra term sitting in here, and it looks a little bit different than maybe it does in your calculus class. So before we use this information, I'm first going to explain this stuff right here at a slower pace. So let's go to the whiteboard. And again, we're basically trying to get this first point. So let me start by being pretty thorough here. It turns out, let's start with velocity. The derivative of position, that's supposed to be a vector, is velocity, okay? So in this case, if we were working in one-dimensional motion, we could actually rewrite this as the velocity in the I hat is equal to the time derivative of position, or the x coordinate, in the I hat. And so again, we're just talking about things moving right or left. This I hat just means to the right. Now, in this case, one of the things almost every mathematician or physicist will do, will look and see if there's anything that cancels out. So immediately we cancel everything out and we get this equation that looks like this. It looks like it's not a vector. If you were not paying attention and didn't realize where this equation came from, you would say, oh, this must be speed and this must be distance. But that is not true. This is velocity in this equation. And this is up here. That's position.
Professor Gerstad?
Yes.
What page is this?
What was it? 43 or so? Something like that.
Word 2.
Oh, but yeah, this part here, I'm just kind of explaining what was on. I'm explaining how I got to the stuff on page 42. So right here, this isn't on any particular page, okay?
Okay.
Yeah, but we're going to be on page 42 in a minute. But the fact remains is velocity is different than speed. And in this chapter, every physicist and student eventually gets used to being lazy here. The fact remains here is this is not speed, even though it might look like speed. It's velocity, and you're supposed to know that. You're supposed to know this x is representing a position. And the short version of this is basically this number could be positive or negative, and so could this, right? You could be to the right or to the left of the origin. You might have a negative I hat. You might have a negative velocity. So when we're looking in here, the whole vector part of this basically is saying this v or this x could be positive or negative. That's the working knowledge that we need. All right, and then similarly, we could do a similar thing over here. Acceleration is dv dt. Well, there's an I hat on here. There's an I hat on there. Working our way down, we would get a, and sometimes you'll see it like this. Sometimes we'll actually put a subscript here to remind you, oh, this is just for the x direction. So we could have actually done that right here too. We could have put a subscript x on this. Sorry, that's messy. We could have put a subscript x right there. So the idea then is that this is supposed to be a warning like, oh yeah, we're talking I hat only here. And so that's a clue that these are vectors, not just scalars, or not just positive quantities. In practice, how can we use this to figure out those integrals? Well, let's take a look. Let's start with that velocity equation. We know that v equals dx dt. Again, these are vectors. I'm not drawing them, but they are. If I want to figure out, let's say, the position from this equation. Let's say I know the velocity and I want to figure out the position. In certain special cases, we can actually do this trick. Cross multiply by dt and switch the sides. So again, all I did was cross multiply by the differential, the dt, and then I switched the sides. This is legal as long as these are both differentials, right? They're not inside an integral right now, so you could do that. Now, in this case, this relates to a derivative of x. If I want to get x, what is the opposite action of taking a derivative?
Integral.
Integral. So let's draw that on here. And this coming up, this next step is where I might differ from your calc books, okay? All right. Now, what is the integral of this term right here?
Is it just x?
No.
Oh.
You would think it's x. And to be honest, that's what most students would say. Really, it's x plus c. You know what I mean by that?
Yeah.
And so you got the function part right, but this constant matters a lot in a physics class. It's a huge deal. Now, in order to avoid making that mistake on test day, this is what I want you to think. So this might be slightly different. I'm going to integrate from t initial to t final on this side. Or sometimes we just say t initial is equal to 0. So maybe we'll go from 0 to some arbitrary final time. Well, over here, what would be the equivalent limits? What do you think would be a good lower limit for an x integral?
X final, X initial.
X final and x initial. I got the idea. Right? And so if we do that, we don't have to think about the integration constant and the techniques. Yeah. Well, now, Gonzalo, you'd never have to worry about it. So this is basically turning this integral into a definite integral. And here is the trick. By doing this, you could plug in the initial position. The final position would correspond to this arbitrary final time. That means when we do this integral, we actually get x evaluated at, sometimes I get lazy and I just write initial and final instead of x initial and x final, is equal to the integral from 0 to some time t final of velocity dt. Now, when you do this one, what do we get over here? When you put in the limits, what do you get?
Delta X.
Yeah, you get delta x. Now, to be honest, in your math classes, usually x initial was 0 for every frickin' problem. In the real world, sometimes things don't start at the origin. Shocking, I know. So in the real world, the integral of dx is actually delta x. And this is confusing if you're not paying attention. But if you stick in these limits, hopefully that makes sense of this. Now, in this case, so that's this side, and I'm just checking here. Okay, now look at this. If I'm clever and rearrange this, I hope you agree, I could actually write this as x final is equal to x initial. So I'm just taking the minus x initial and bring it to the other side.
Could you pull it up?
Oh, my bad. Thanks.
Thank you.
Yep. Thanks for the shout out. Then we get this, right? And sorry for the glare here, doing the best I can. So in this case, x final is equal to x initial. I just brought the x initial to the other side, and we're going from 0 to t final. Now, don't overthink this. What have we really done? What I'm saying here is if you tell me what value you want for t final, I'll tell you the position. That means this is position as a function of time, essentially, right? Now, it doesn't quite look right, and I'm going to explain why. There's one subtle thing right here. I can't help it. I like math. we see that there's a t right here. Notice I call this t final right here. It's because I don't want to have the same symbol in the integrand and in the limit. Otherwise, you have a circular reference. So what I usually do with this problem is do the integral, then immediately after doing the integral, I change this to x of t.
Could you scroll it up, please?
Oh, yep. After doing the integral,
Thank you.
I set t final to t. So there'll be some crap here with t's in it. And so the idea, again, is you do this integral from 0 to t final. After doing the integral, change all the t finals to t, and this is essentially the position as a function of time. Now, if you look, give me a sec. That's what this equation is right here. And notice this is what I'm saying right there. Obviously, something similar would happen here. The only difference is you're going to start with A equals dv dt. So far, none of this is earth-shattering because everybody in this class should have had calculus already, and you should probably know this. But there's a catch. This doesn't always work. Okay, so this is where physics starts to relate to reality more than a math class. I want to point out there's a huge if statement right here. If acceleration is a function of time, you can do this, right? It has to be a function of time to plug into there. Here, velocity has to be a function of time. If they are not, this process may not work. Okay, I will explain what you can do if those things aren't true after we do a worked example. So I'm going to pause for a sec, see if there's any questions. What do you think? So far, so good? Okay. Let's do a real example. That way we kind of see how these rules apply and the ways you might get caught up on a test question, things like that. So let's get back into here. All right. And so let's see. Why don't we just start easy? Let's just do 2.39. Okay. So we're going to work on 2.39. Again, this is on page 42. So we're going to look at 2.39 on page 42. I'm going to try and get this whole thing on the screen if I can. Hold on a sec. All right. Sorry about that. All right. So I'm going to get my board erased and write down some facts up here, and then we can work through the problem together. Okay. Don't forget, you have the solutions. If you don't want to go at my pace, if you want to go faster or slower, you could always work with the solutions. That said, I try to aim for the, like, at the middle of the road for the tempo, or maybe even slightly slower than that. So remember, you have the solutions. You can go through and read the answers before if you don't want to work at my pace. And I'll go in there. So I'm going to, let's see, I'm going to write down the problem number, 2.39. We were told, I'm going to ignore all that I hat crap. I'm going to ignore a lot of units and sig figs. Oops, minus 3t squared. All right. So we know we're looking at something moving in the eye. I'll throw it in just because it's right there. It's not too much work. But I do have to hide sig figs just because I'm running out of room. Okay. The first question says, what units are implied? So let's go to here. Okay, we have this equation. Part A says units on each term. All right. Well, tell me anything you know about this stuff. Like velocity. Do we know anything about the units of velocity?
Meters per second.
Yeah, probably. We expect this side should be meters per second. And just so it's a little bigger, I'll scroll back later when we need it. All right. So we expect this should be in meters per second, right? So what does that say about this term?
That's 2 meters.
It'll be meters per second.
Yeah, it also has to be meters per second. Remember, if this side, if the output is in meters per second, everything on the other side has to have units of meters per second. Well, let's look right here. We're going to have the units of 8 times what are the units of t usually?
Seconds.
Seconds. That has to equal meters per second. So what are the units on 8?
Meters per second squared.
Yep. And similarly, I hope you see that this one should be meters per second cubed, right? I times it by 2 seconds. Did I get that? So this one should be meters per second squared times seconds. And so we see, oh, go ahead.
What does the I hat and like J hat, what do they mean?
I hat means to the right. J hat means up. That was in chapter 3. So yeah, we can review that on the break or in office hours tonight. But for now, all that means is I hat just means it's a right left problem. J hat means it's up and down problem.
Oh, so like negative I hat would be to the left?
Exactly.
Okay.
So the mathematical definition of I hat is literally to the right. It just saves us time writing to the right all the time. So negative to the right would be to the left, as you said. Absolutely. Good work. All right.
Thank you.
Okay, so there's the units on each term. That's part A. Let's go back. And okay. Take a second to think about this. While I get my board erased here. We know the units now. Is it appropriate to use this equation? What do you think? This is an equation some of you probably saw in high school physics or in Physics 110, and we used it all the time. So what do you think? Can we use this equation?
We're not given the acceleration unless we find it.
Okay. Could we find it?
Yes.
How could you find it?
Taking the derivative of the velocity.
Aha. So what he's saying is, whoops. Oh my gosh, where's my mouse? There it is. We could get the acceleration from there by taking a derivative, right? So all we have to do is take a derivative from here, figure out the acceleration, and plug it right in there. Does that work? What do you think?
Yeah.
I hope.
No, it does not work. So why does it not work? This equation applies to what special situation? Do you know?
Would it be for acceleration?
What kind of acceleration?
Oh, constant.
Constant.
acceleration?
Yeah. This applies to constant A. And just look, if you take the derivative of this, the first part of what Jacob said was true. You could take the derivative. When you take the derivative, will it be constant? Will it be a number? Or does it have t's in it?
It's teasing it.
T's in it. So A is not constant. Don't use this equation. That equation is great if acceleration is constant. It's no longer valid. So there's one thing we have to watch out for. We're so used to using this all the time. It's not always valid, only when constant acceleration. Good job. So let's say we've knocked this one out and this one out. How about this part? Let's compare the initial speed to the initial velocity. How do I get the initial speed or velocity anyways? What do you think we should do? How would you get that?
Plug in time as 0.
Mm-hmm. And then, all right. If I plug in t equals 0, what do I get? -2 I hat. Now, again, I'm being lazy with sig figs and units. We know they are there, but we're just not writing them. Otherwise, it's going to take us all day. So at some point, yeah, on your final answer on a test, you would probably write the units just so you don't lose them. And if you're curious, you can write these two things in either order. Okay. You could write it like this. So what did I just write down there? Is that a speed or a velocity or both?
It's a velocity because you have a direction.
It's a direction. So it's got a direction. So it's a velocity. What is the speed? So this is, I'm just going to write VEL right now, which is actually this symbol, V with the arrow. Gets confusing. What's speed in this case? Somebody other than Jacob.
-2.
No, is it
They-
just regular 2?
It's just regular 2. It's the absolute value. So we have to watch out for this. And this is something you need to look out for in physics problems. Sometimes we'll talk about velocity. Sometimes we'll talk about speed. And you need to know if I ask for speed, I expect you to remember the absolute value. If I ask for velocity, I want the plus minus sign. So this one is always positive. This one is sometimes positive, sometimes negative. Go ahead. Question? Okay.
Sorry, I'm trying to find this the workbook and I can't find it.
Well, yeah, it's because you have to buy it, right? There's no
Oh,
more free chapters online. So now the solutions are online. This was mentioned the week before class and last week. So not to bust your chops, but I'm going to bust your chops. All right.
it should be coming in like.
Oh, okay. Gotcha. Well, you've got it on screen now. You do have the solutions already. So
Okay.
yeah, that's good. Okay.
Sorry.
No, you're good. Yeah. So in this case, and my reason for doing that is literally because I want people to have the paper copy. So that's one less screen you're scrolling through. And I really do believe that's a good idea. So that's the reason I'm not just giving you the PDF all the time. All right. And in face-to-face mode, it worked really well. Well, welcome to online learning hell. Okay. That said, I think we beat this one. We've done this one. We've done this one. How do you get the magnitude of the initial acceleration? Any ideas? What process would you follow to get this?
Square root.
Square root?
Derive the acceleration and plug in 0.
Okay. How do you derive the acceleration?
Take the derivative of velocity.
Yeah, that's the right phrasing I was looking for. Yeah. So take the derivative of velocity to get A. So that's right here. I think you could do this. We could take the derivative. You could do that. And then it says initial. So then you have to remember to plug in t equals 0. And then we would get it, right?
You have to take the absolute value.
Yeah. So let's do that one. Okay. We have to at least think about the absolute value. So in this case, let's say, what part was this? D or C or something? I forget.
RT.
D? Okay, thanks. So we know that A equals dV dt. Again, I'm not drawing the vector arrows here, but we know they are there. There's an implied I hat on both of these, and they just cancel out all the time. So when I do this one, that's going to be, when I take the derivative of 2, it goes away. What do I get? 8 minus 6t. All right. Now, obviously, we know the units already. We know the I hat is there, so this is done. Now, in this case, it asked for initial accel, and it asked for the magnitude. So that means plug in t equals 0, then absolute value. Now, in this case, either way, we get A initial equals 8. Obviously, I'm not writing the units again, but we could for our final answer just to make it look pretty. And then if you want to, we could stick back on the symbols at the end. So this is kind of the trick. You ignore all the units and I hats and J hats, and then at the end we stick on the vectors and the units for our final answer, so it looks pretty and makes more sense to a reader or a teacher or a friend or whatever. Okay. So in this case, oh wait, this is not what we want. We want the absolute value of it, which gets rid of the I hat. I should be careful. I wrote down the acceleration, but we want the magnitude. That means take the absolute value of it. All right. Now, if you're taking the absolute value of a vector, if you don't know this, usually you use 2 absolute value lines rather than just 1. This is called vector norm. Anyways, whatever. You'll learn about that in Math 183 or something, maybe. Okay. All right. Let's get back to it. So that takes care of, done this, 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 this. Now we're right up to here. We are told this new fact. Jerk is the time derivative of acceleration. Determine the magnitude of the initial jerk. All right. Well, there. I think that's pretty straightforward. So we say that jerk is dA dt. Again, I'm getting lazy with the arrows. And then what was A? Oh, right there. What is it? 8 minus 6t, which is just going to be -6. Aha! Sorry for the glare. So in this case, we know that the jerk as a function of time is -6. It's a constant. So notice the initial jerk is also -6. So did I answer the question?
Why is this one not absolute value?
That's what I was asking. Nice job. So I did not ask for the jerk. I asked for the magnitude of the jerk. So the magnitude of the jerk would be the absolute value, which would be 6. What are the units? Hint, read this equation and figure it out.
Meters per second squared or cubed?
Yeah. A, if you look, you can use this equation to figure out the units. This is meters per second squared, and this is seconds. So shouldn't this be meters per seconds cubed? So jerk is not just a term used for your physics instructor. It's also an attribute of motion.
I had a question about like the double bracket, not the bracket
Yeah.
out, but the double absolute value.
Yeah.
What does that mean?
It just means absolute value of a vector.
Oh, okay.
So if you take absolute value of a number, you use 1 line. Absolute value of a vector, we're supposed to draw it with 2. If you drew it with 1, hey, it's not going to bother me, dude.
Okay.
Now, a mathematician, you know, somebody being very rigorous. I'm a mathematician too, but not in this class. I'm like trying to, I'm just doing anything I can to help you learn. All right. So you could do single line, double line, but traditionally for vectors, you use a double line. Good question. Others?
Why wouldn't it be -6?
The jerk is -6 in the I hat.
Uh-huh.
The question asked for magnitude of it. Look back at the question. Let me get it in here. So if you look at the question,
Yeah, I got it now. I got
you
it.
got it? Okay, cool.
Yeah, thank you.
All right.
And would we put in the I hat for the bottom?
You tell me. Does a magnitude have a direction?
Yes.
No.
No.
So this is a little subtle thing. And so magnitudes of vectors do not have direction. A vector
Okay.
is something that's size and direction.
Okay.
And so this is saying, what is the size of the jerk? So
Okay.
now, yeah. Magnitude is not the absolute value of a direction. Magnitude is the absolute value of a vector. And what that does is it gets, in two-dimensional motion, it's more complex. We will discuss that later. But in one-dimensional motion, it serves to get rid of any minus signs and any I hats or J hats if it was going up and down. So in one-dimensional motion, that's what the magnitude does. It's the size of the number and the units with no plus minus, no direction. Good.
Thank you.
Yep. Good questions, everybody. Like it. All right. Now, think about this. What does jerk mean physically, right? You probably have some intuition. Imagine you're sitting at a stoplight in a car, and then somebody steps on the gas. Your acceleration changes from nothing to something. There was a change in acceleration, and the car jerks forward. Seems reasonable. Or what if you're driving along at constant speed and then they slam on the brakes? You jerk forward. You feel a jerk when you have acceleration change. And so that seems plausible. That's kind of, I think, at least that's how I remember the name. I don't know if that's the origins of it, but that's how I remember it. Question? Oh, okay. I thought I heard somebody unmute. Now, all right. Great. Let's go back and see where we're at. Okay, where were we? Okay, we figured out this crap. We've done parts A through E. So look at this. We're getting close here. I think part of it we actually have already. So we're trying to get part F. We've got the equation for the acceleration of time already. And then now we want to get this position as a function of time. So just rearranging this. Let me get up my whiteboard again. All right. Okay, so in this case, we know how to get the acceleration. That's easy. What do I do to get the position?
Integral.
Okay, so what am I integrating?
The 8 minus 6t.
Okay, and so you're telling me that, now careful, that's not quite right. The acceleration is this. What is the equation that relates position to acceleration or position to velocity?
Is it the derivative to respect of time?
Yeah.
Is it like,
This is the equation that helps us relate x to velocity, right? So then let me ask you this. If I want to get this right, can't I just rearrange this to say dx is equal to v dt? And then can't I just integrate both sides here? And won't that basically give me x is equal to the integral of -2 plus 8t minus 3t squared dt? Basically plug the velocity in and integrate it. Isn't that going to work? What do you think?
Would there be no plus c in the x?
Good job. This is wrong. I was looking to see if you caught it, and you did. Remember what we said? When you integrate it, what do you have to do? Limits. Otherwise, you have to think about the plus c. Nice job. So here, we're going to go from x initial to x final. Here, I'm going to go from 0 to t final. And remember, after we do this integral, we can change t final back to t. X final is what we're looking for. X final will end up being the position as a function of this arbitrary time. And again, the only reason I'm not making this a t is because I don't want to have t's in the integrand and the limits and have a circular reference, which is technically not what we want to do mathematically. Okay. So then what do I get on this side here? Moving it over. Whoops. Okay, let's do this integral. -2 minus 2t This one is going to be what?
4t squared.
Right? And then over here, I think we're going to get minus. I'll leave the 1 in now. This is going to be t cubed over 3, which will cancel that. And then don't forget, we still have to put in the limits from 0 to t final. When you stick in this 0 limit, it's going to drop out. That's not always true. Sometimes when you stick in the 0 limit, you get a number. Okay? I cannot stress that enough. Make sure you always check the 0 limit. At least look at it and be like, should it go to 0 or not? Here it does. All right? And just to be clear, I'm going to put that in there. Crap, what's x initial? Do we know it?
It says 2 meters to the left of the origin.
So what does that do? What does that tell us? Let me show everybody, Jake. Give me a second. He's looking right here. The initial position is 2 meters to the left. What does that tell us? What does that sentence mean?
That it's -2 meters.
X initial is -2. Now, obviously, it should be -2 meters I hat, and I'm just getting really lazy when I say -2. And this should have a vector over it. But man, okay. So that tells us this right here is -2. Now, in this case, I'm going to get really lazy. We already checked. When I plug in the 0 limit, everything drops. When I plug in t final, I'm immediately going to change it all to just t's anyways. So in this special case, you get this equation. Polynomials are pretty easy. All right. Now, in case you're wondering, we've actually derived a new equation of motion. Look at this. This is x initial. This is v initial x. This is a initial x. And what is this? Wait, this is 1/2 a initial x. How about I write ax over 2? And what is this last term right here? Jerk over 6.
And what
Sorry.
happened to the t final and the 0?
I stuck in the limits, right? If you stick in 0, drops, drops, drops. If you stick in t final, these are all t final. And then I'd rewrite them all as just t because it's annoying writing the subscript. So again, the trick is do the integral, plug in the limits. After you plug in the limits, rewrite t final in terms of t, just so you don't have to write so many subscripts in subsequent problems.
Okay.
Good. This is the equation of motion for constant jerk. So if you had a problem where acceleration wasn't constant, but jerk was, this would be your new kinematics equation. You could imagine, what if it was some other powers up here? You could have the next derivative. I think there's a joke on Wikipedia. The next derivative is snap, then crackle, then pop. So you could just go on till you're blue in the face writing and describing these things. But yeah. All right.
A quick question. Sorry.
Sure.
Why is the acceleration and jerk like on top of why is acceleration over 2 and jerk over 6?
Well, take a look. If you did this, come back to here and do this. So if you just start, let's say A equals J naught, whoops. We know that jerk is equal to the time derivative of acceleration. Let's say jerk was a constant, J naught. Well, when you integrate this, flip it around, you're going to get A is equal to A initial plus jerk times time, right? Integrate it to get velocity. You'll get a V naught plus A naught T plus 1/2 jerk times T squared, right? When you integrate that, when you see where I'm going?
I think so.
You integrate it again, well, you got a 1/2, but you also have a 1/3 from the second integral, right? And so when you integrate these, if you had a constant here, when you integrate, the equation changes. Now think about this. Does this make sense? If
Oh,
jerk is
because-
0, you get back the same crap you used to have.
Oh,
Seems
okay.
plausible.
Yeah, I get it now.
Yeah, it's just calculus.
Going from acceleration to velocity,
You have one more integral to do now.
so that's where the squared comes in. Okay.
Yeah. Cool. Yeah. Now, again, the particulars of this problem or any one problem is not that big a deal. We're looking at your ability to follow instructions and pay attention to details and deal with units and the phrasing and read questions carefully and look for stuff in the questions. Why? Because someday there might be a problem you actually do care about that relates to your job, and it's going to be your job to pay attention to all these little details that sometimes show up in a real life question. Did you read everything carefully? That's really all this is. Because the integrals you're probably pretty good at, right? All right. And if not, you'll get good at them. Let's go back and see what I forgot to talk about. Okay, so we did this. Okay. Okay. It says, during what time intervals, if any, is the object moving to the right? Now, Jacob's been answering a lot of questions today. I'm going to tell him to clam up. So, Jake, you can still think in your mind, but try not to blurt it out. Let's let somebody else have a shot here. What do you think? Does anybody have any ideas here? Thanks, Jake. What do you think?
Anything longer than 2 seconds?
Why do you think that? I guess give me an idea of what's the process in your mind so I could try to, like, what process might you attack this with? You don't have to tell me the answer, but
We started 2 meters from the left, so we were trying to get to the right, past the right, correct?
Okay.
So then I'd plug in, I just kind of like guess and check, plug some seconds in to get to zero first.
Okay, now be careful here. This is the initial position, X initial. This question is asking moving to the right. When it asks that question, what does it mean to be moving to the right?
The displacement.
Positive I hat.
Okay, so you're saying delta X has to be greater than 0. That's true. What's another thing? If you're moving to the right, what else has to be greater than 0?
Is it that velocity is positive?
Yeah, just so what we're asking, this is a fancy way of asking, when is the velocity positive? Now, describe one method you might use to figure this out. Any ideas? Anybody? Any ideas other than Jacob here? I'll give him a break.
Would it be just setting the equation to 0 or something?
That's a great idea. If you set the equation to 0, if I set this equation, let me get some cleanup here. Sorry, it's getting messy. Let me get my marker back. If I set this equation equal to 0, then what?
You'll find the points at when it changes to positive.
Oh, okay, so what am I solving for? Solve for
Final velocity.
uh,
Or is it
solve
slope or something?
t.
Oh, t.
And that will give us the times that it's equal to 0. Do you see what I'm saying?
Yeah.
So you're right. Set this equal to 0, and I think you probably knew exactly what to do. You just didn't quite phrase it right. So you set this equal to 0, solve for t, and those are the times that it's equal to 0. How does that help us? By the way, I did that in my mind. I'm going to calculate it. One of them is approximately 0. I think it's 27, or maybe it's 28. And the other one is 2.4 seconds. Let's say I did that. I had to do the quadratic formula, and I get these 2 times. So let's say I did that, and I figured it out. I'm confident you can do that. I'll show you through in the solutions if you need it. But let's say we did that. How does that help?
Does that mean at 0.28 seconds, it'll
At
change?
0.2 seconds, yeah, it'll change. Absolutely. How does that help us?
After that, the velocity is positive and it moves to the right.
How did you know it had to become positive? That's is that Alonzo?
Yeah.
Yeah, Alonzo, great job. You're right. How did you know it had to change to positive? What clued you in?
Where the time in the equation for velocity. The
Okay.
coefficient is positive, or yeah.
All right. How about you got it. So let me see if I can make this make more sense. We already know V initial is negative, right? V initial is -2. Because if you set those times to 0, we get -2. So we know the initial velocity. Then we know at 0.28 seconds, it's going to change. So that means it's going to move forwards after that. So V from 0.28 to velocity 2.4 is greater than 0 because it changed at this special time. And then it's going to change back. So for this problem, it's moving to the right whenever V is positive. So that's right there. Great job.
This could be related to like the first derivative test. Like, for example, when you're graphing something and then you want to know when it's increasing, when it's decreasing.
Yeah, we could probably figure that out because this is essentially the first derivative test of position. Agreed?
Yeah. Agree.
So if you had the function of x, it's the first derivative test on x. That's another great way. Any other ideas? There's another classic technique you could use for this.
You
Is
could
it
graph
just-
it.
Graph it. Right now, I'm not going to do this all, but you could actually come in here and type in the numbers, right? -2, whatever, 8, -3. Then you could come down here and make a column of time data, 0, enter, 0.1, enter. You could make this column of time data. And then you could say, oh, well, this is equal to, et cetera, and go through this thing and plot it. Believe it or not, that's what we're going to focus on in lab. So in lab, I'm going to show you how you could do this with all the plotting methods. And then the idea is hopefully you'll understand how to do it with a plot, and the plot could check your work from doing all the calculus. And so if you get good at this, it becomes very fast to plot this. Some of you probably know, oh, well, there's a free software program I could use online to just integrate this as well. I like you to learn at least some I don't know, I hesitate to call it coding, but yeah, you could learn that way too. But so great. So just let's check the solution, see if there's anything I forgot here. All right. So this is these are the actual numbers I ended up finding out. And so again, you could supplement that knowledge with a plot. So cool. How about here? What is this question asking us to do? What do you think? What is that question asking us to do?
Is it to go back to the previous, or to go back to the equations that we have derived and
Yeah.
plug in 3 seconds?
So let's see. We know x of t, we know v of t, and we know a of t. So should we be able to just plug in t equals 3 and we're done?
I hope. I'm just kidding.
And it's not quite right. You could do that for this equation. You could do it for that equation.
One's a magnitude.
This one is a magnitude. So you got to remember this one, we're going to have to take the absolute value of. Don't you love physics? Imagine doing a whole bunch of work and then you forgot to check the absolute value and you missed some points. Welcome to physics. All right. But hopefully that made some sense. I'm just trying to trick you now so that you don't get tricked on test day. That's why we're doing these. Hopefully this is helping. All right. Next. And so, let's see. There's something in the chat there. Right on. Okay. So what do you think? How would you get this one?
Would you use the acceleration?
No, I wouldn't.
Isn't it the magnitude of the position?
That's closer. So let's talk about that. So basically, don't we know X? I'll call it X3, meaning X at 3 seconds. We know that number from part H. We know this, right? We could plug in 3 into the X equation and get it. Okay. And don't we also know X at 0? I think we know that. That's -2, right? And again, I'm leaving off the units and the I hat. It's to the left. That's why it's negative. So then I forget who that was that unmuted. What do you think we should do here? Just kind of describe how you would get it. You don't have to tell me the number.
The numbers or the concept? Like
Yeah,
I
the
would think,
concept.
like I would think getting a X final minus X initial to like whatever we get for X3 minus X initial.
Do you think I might need an absolute value on that?
Yeah.
Yeah. Turns out that's not right either.
Oh,
You're
really?
close. Now, you see what I mean about physics being trick? It's like you guys know the basics, and that was a great answer. That's what I was expecting you to say, but there's a trick. Remember, this thing starts out moving left, turns around, and then it comes back. We need to split this into chunks and do exactly what you said for each chunk separately. Let me show you in the solutions. It'll make more sense if I just show you. Right? The idea is this. It starts out at this position. Sorry, I screwed up in italics right there. That's my bad. Okay. So it starts out, and then for the first 0.28 seconds, it moves to the left. Then from this time to this time, it ends up moving to the right. And then finally, it ends up moving back to the left. Or look at this way. On the time interval, it changes position this much, so its distance is the size of that. Here, it changes position this much, so its distance is that much. Finally, it does that. Now, I know we haven't talked about graphs yet, but I think this will make a lot more sense with the graphs, which I happen to have for you here. Let's scroll down. I love this. Ugh. That sums up physics, doesn't it? Now I'm going to try and blow this up just a little bit. Let's go one more if I can. Whoops, that's too much. Let's try 250. Let me see if I can get this all on screen. There we go. And maybe just a hair this way. Okay, so look at this. This is actually a plot of the position versus time. Remember, I will show you in lab this week how to make these plots. So you might not know how to make this yet, but I'll teach you. It starts right here, and then it goes down a little bit. That's this first phase. Whoops. That's this first phase right here. So delta x, it changes by negative 0.27. Okay, and that's about the first, this time I think was 0.28 seconds. Just a coincidence, the numbers are so close. So in 0.28 seconds, this thing goes down 0.27 meters. Next, from right here to about right here, this is 2.4 seconds, right? So during this time, it's going to go up what this number is. So delta x is equal to let's say 4.7 meters or so. I'm just getting lazy. And then finally, it comes back down a little bit. delta x is negative 1.4, let's say. Now, again, I'm being lazy with sig figs here, but I just wanted to point out there's a small amount of negative motion at the beginning, that red stuff, then it goes forwards. And here we see something very confusing about this graph. We are talking about a particle, give me just a second here, that's moving in the I-hat direction, right? So in this case, up and down corresponds to I-hat motion. So as you go higher on this plot of position, remember there's an I-hat implied. The horizontal axis is time, and this is the next thing we need to talk about, is how to understand this graph. So I'll go into all the details on the graphs in just a minute after we take a break probably. But I just wanted to point this out. Hopefully you agree that if you can learn how to read graphs, it will help you understand some of the concepts that are tricky. So it's kind of a package deal. The better you get at all of it, the better you understand. And just while we're at it, let's look at all the plots. So this is what all those plots look like. And so here we see acceleration is clearly not constant, right? The acceleration plot. And to get from here to here, you're taking a derivative. V is dx dt. And then to get from here to here, you take another derivative. This is dv dt. And like we were saying at the beginning, whoops, if you're going this way, you're integrating. So we know that v is equal to v initial plus the integral of a dt. If a is a function of time, which it is. And here, to go this way, we know that x is equal to x initial plus the integral of v dt. If v is a function of time, which it is.
Is there no plus c?
If we've done the integrals while we stuck in the initials and finals, effectively, this is like the plus c, right?
All right.
And
Yeah.
so this avoids us having to think about that. Now, I want you to be careful. This technique works for every physics problem, right? If you are doing a calculus method where you use the plus c's and you sometimes put it on the right side or whatever, it can get sneaky. So let me just leave it at that. I like this method because it forces me to do things correctly. Let me just say it that way.
I did have a question.
Yeah.
So basically in this class, we don't use C's at all, right?
No. Yeah, you could. And if you do it correctly, I'm going to give you full credit. But yeah, I think it's easier just to use definite integrals and not think.
Yeah.
Right. I just want it to be automatic for you. So I'm trying to find a procedure that is automatic. And this is as automatic as I felt I could make it.
Okay.
There are other correct ways to do it. And if you do it a different way, that's not the way I'm showing you. Hey, full credit. Good comments. Yeah. Others. All right. We should probably take a quick break here. Let's see if I finish this problem. Always good to check that last. Let's see if there was anything left. Okay. All right. So I will show you how to do this in lab on Thursday. This is a good time to take a break. I do want to point out there's some other problems on this page. You can go through and practice them. And then it even gives you some more over here. So I've got a lot of these. If you're bad at these, there they are. And I forget who that was that asked about the constant jerk equation. If I just scroll down here, remember to search through my PDFs. You could just, let's do 2.53. Oh, let's do the next. Here's that equation. If you're wondering, what do you get the equations of motion with constant jerk? Here it is in more detail. Okay. So here's some that have a cosine function. Here's some that have exponentials. All right. And mixed. So I think you've got all this stuff here if you need it. All right. Okay. Let's take a quick break, 7-8 minutes, something like that, and then come back. I'm going to get some more water and maybe use the restroom. So I'll see you guys in a minute. I'm going to keep the live stream running just so it's all in one file and I don't lose it. So, all right, I'll talk to you in a couple of minutes. Oh, there's a couple questions in the chat here. Okay, got it. Right on. Okay. Okay, see you in a minute. right. Probably get started here in just another minute. If anybody has any questions, go for it. Still got another minute. I don't even remember when we left for the break, so. Let me see what I wanted to do next and get that ready.
Do you want our homework problems to be in order, or can we kind of work?
You can work on them in any order you want. My thought was hopefully you could try and reorder them afterwards so that they're easy for you to find. So in that sense, maybe, I know this seems kind of crazy, but if you want to make it easy to reorder them, just do one problem on a page for those ones that are out of order. And then you could easily just kind of move them around after the fact. It's kind of, I don't know if that helps, but, or if you're doing them on a tablet, you could cut and paste to move them easy. Is that good? Was that Dina?
Yeah.
Right on. Yeah. The thing is later on, there might be a question on Canvas quiz or in a oral exam where I say, find this problem. And the faster you can find them, the easier it is and less stressed out you are. That's it. Cool.
Yes.
Right on. Okay. So let's go ahead and get back into it here. And let me share screen and show you where we're at. So we talked about this plot, and you notice I was kind of going on and on and on about it. It might be nice if we could actually have a general strategy for attacking plots rather than me just telling you some interesting facts about one plot. So to that end, let's see what page I want you to go to. Page 31 in the workbook here, page 31. Okay. And I know I'm skipping all around. I'm actually kind of going through the chapter backwards, but remember, you've got the live stream, so you can watch it again later if you want. Okay. And I think I gave a link in the Canvas module to where those live streams end up, so you can check that later, or you can chat about it after class. Oh, go ahead. Was there a question there? Oh, okay. All right. Gotcha. All right. So I know this is going to seem really crazy, but in general, we want to understand plots, not just these ones. So we have to start somewhere. These are a great place to start. That's what I'm saying right here. So we're going to use time on the horizontal axis, and we're going to talk about position versus time, velocity versus time, and acceleration versus time. Now, notice that those are all vectors. They're all vectors. So basically, if you have a problem where it's moving right, left, that would be an I hat is implied on every number. If it's moving up, down, then a J hat is implied, okay, on all those numbers in the chart up and down. Now, the first thing, we tend to focus most on XT graphs and VT graphs. I know this is going to seem silly, but I'm just going to go to a random problem here in a minute. The very first thing you have to do is look at the plot and figure out, am I dealing with an XT or a VT? AT is down here as well. So what type of plot do you have? You know you have page 31 in your workbook to help you. So make sure you identify the correct type of plot before you waste time doing any thinking. In particular, the slope on an XT graph is velocity, whereas the slope on a VT plot is acceleration. So I see this every year where some student does all the right thinking, but pick the wrong type of graph and they miss every single answer. So it's really frustrating if you pick the wrong type of graph for you and for me. All right. And again, we've seen this a couple of times here. Watch out for vectors, right? X is position. And we've seen this. Remember, the integral of dx is not x for this class. It's delta x, right? And so that's a change in position, which is displacement. Those are the kind of the highlights. Now, I want you to kind of keep all this stuff in mind. If you don't have your book right now, do a quick screenshot right now, okay? And then you can use this in the meantime if you're wanting to follow along. So you could do a screenshot. If you have two monitors, if you're lucky enough to have that, you could throw that up there. And that way you've got these rules if you're playing around with it. And then notice the AT curve. The main thing that we're going to talk about here, the area under the AT curve is change in velocity. Now, to be clear, this is something, I know this seems obvious, but notice the value of V on a VT, let me get my other marker here, sorry. If we're on a VT graph, the value of V is V. If you're on an XT graph, the slope is V. And that's probably one of the more common ones people screw up. You know that slope of an XT gives you velocity, whereas just reading the number off the graph gives you velocity on a VT plot. Now, if we come down to here, and here are some more facts, just some phrasing. You're going to see me using these words. Moving forwards usually means plus I hat or plus J hat. Moving backwards is going to mean negative J hat or negative I hat, okay? Now, the velocity here, let me just kind of highlight some information here. The sign of velocity tells you whether it's moving forwards or backwards, okay? So that's what gives you this information, the sign of velocity. Now, where it gets tricky is the relative signs of these two. Both of these things combine to tell you whether it's slowing down or speeding up. And I can prove that to you in a minute, but basically, if A and V opposite, read this right here. Speeding up or slowing down depends on the signs of both acceleration and velocity. If they're the same sign, it's speeding up. If it's opposite sign, it's slowing down. Now, this is a whole bunch of words. Let's look at this carefully here. All right, so here's a random plot that I made for you. I'm going to hit playback on this. Now, right now, I want to show you something. Watch the guy, and all in particular, what I want you to do is I want you to look at this graph and this graph down here. I want you to compare these two graphs and the signs of them. Now, when I do this, I'm going to hit pause occasionally. So let's just, actually, the first time I'm just going to run it and let you see this whole thing. And let's run it at high speed here. Okay, here we go. Moving forward, slowing down, moving backwards, speeding up, moving backwards, slowing down, moving forward, speeding up, moving forward, slowing down, etc. We see that all the different types of motion are here. All right. And so let's look at this again another way, but run it slower. I'm just going to talk and describe things. Again, I'm looking at these bottom two graphs. I'm looking at right here is a 0, and this is a 0, and this is a 0, and this is a 0. So notice in this region, velocity is negative. In this region, velocity is positive. And then now let's look down here. Here, A is negative. Here, A is negative. Here, A is positive. And so we could see right about here where I made this change, right? And maybe even right here, the type of motion might be different. So let's watch this again, at least the first few seconds. And let me get one more in here. Here, A is greater than 0, and here velocity is greater than 0. So we can kind of see all four regions if you look at it carefully. Again, here, when you have velocity negative, that means moving backwards. So here it's moving forwards. Sorry for the abbreviation, just trying to get this done. This is moving forwards. So, and here it's moving left, right? Because the value of V is negative right here, 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 here. The slope is not negative in every case. Here, the slope is negative. Over here, the slope is not negative. So let's run this back again. And let's just focus on the motion here. Here we go. Notice right there, the guy is moving forward. So if you didn't see this, I'm actually watching this guy up here move around. Okay, so I'm watching this as guy moves. Notice right here, he should have a positive velocity. The acceleration is negative, so he should be slowing down. Go ahead. Question? Okay. Slowing down. For a split second, he stopped there. Now look, moving to the left and speeding up. Now, still moving to the left, but the acceleration just flipped sign. I'm showing you where we're at right here. The acceleration just flipped. I still have a negative velocity. Okay. Slowing down. Right at that split second, it was stopped. Now it's going forwards and speeding up. So we see that you can actually learn a lot about the motion of this guy up here by just seeing the graphs. And my goal is for you to be able to see these three graphs and imagine what the particle is doing up here and be able to describe it in words and equations eventually. So we want to be able to go back and forth between equations, the actual images of objects moving, and these graphs. That is the goal. All right. I'm going to pause for a second. Any questions on this? It's a pretty complicated one. I'm going to redo it with a simpler one. All right.
I did have a question on the acceleration
Sure.
graph.
Yeah.
Because I understood the velocity one, but like the bottom one, how it was like just straight and then it goes up.
Yeah.
But like the direction that he was going, it just, I don't know. It didn't really.
Okay. So you can't see the acceleration up here. Well, let me rephrase. You could see it if you look at changes in the velocity. Okay. So watch this right now. And we're going to look at the first few seconds of motion. So we're just going to look at this time right here. And this time right here, okay? The idea is velocity is positive, acceleration is negative. As a result, the velocity is getting smaller. It should be slowing down. So that's what the guy should be doing up here. We should see the guy up there slowing down.
Uh-huh.
That's how you know it's accelerating to the left.
Oh, okay.
Just afterwards, when he turns around, he starts speeding up. Well, this is velocity is negative, and we see acceleration is also negative. That implies he should speed up. So let's just look at that. And this is getting so messy. Let's do this again. Ready? So here we go. Right? Slowing down. And then right here comes to rest for a second. See how the guy's just standing still for a split second?
Huh.
Now it's going to speed up to the left.
Oh, okay.
And now I'm going to pause. At this point, the guy is moving left. The acceleration is going to flip to positive. He should start slowing down. See it? Slowing, slowing, slowing. Now he comes to rest again for a split second. And now velocity is going to be to the right and acceleration is to the right. He's going to speed up. Is that helping?
Yeah, a little bit.
Yeah, it's a lot. And there's like, oh, so if you want to do this, let me, it can help to play with this yourself. So if you Google Phet moving man, if you want to get that should get you this simulation. And I run it as a Java simulation, even though there's security issues, because I've been using it for, I don't know, 20 years. So I recommend playing with it yourself. And here's what's cool. So let me clear all this and let's do a simpler problem. Right? Let's say you start out at -5. Let's say your velocity is +6 and your acceleration is -4. If I run this thing, it's going to be a simpler motion. Moving forwards, slowing down. Now he's moving to the left, speeding up, and then he crashes into the wall and comes to rest. Now you can't really see this acceleration here because it's too high off the charts, but whoops. We can actually analyze this motion in playback, right? At this point, I'm going to pause. The person is moving to the right. This is a positive velocity, moving to the right, moving to the right. Here it's a negative velocity, moving to the left. Here it's still a negative velocity, moving to the left. Now, the trick is you could think of this as zero speed. This is, let me say it this way. This is the speed equals zero line. Anytime you're going on the velocity graph now, if your line is going towards here, you're going towards zero speed. Here, the initial speed was 6. At this point, the speed is the absolute value of -5, which is +5. So right here, the speed is 0. And so you can kind of see the speed is your distance from the horizontal axis on the VT plot. Velocity is the distance and sign from the 0. Now notice what happens right here. The acceleration was a constant value until the guy smashes into the wall. Well, when the guy smashes into the wall, he's moving this way. A second later, he stopped. So velocity went from a negative number to 0. If you go from a negative number to 0, you must have accelerated this way. And because you go from a large negative number to 0 very quickly, we see there's this huge positive acceleration there that's so big you can't even see it on the chart. A last note, notice the concavity here. If A is less than 0, concave down on the xt plot. Okay, so if you have a negative acceleration for the whole problem, a constant value, you're going to get this max. So you could actually go into here and try a different motion. Let's try one more, and then we'll get to the doing some problems here. Whoa, I lost my mouse. There it is. Let's say we start out with 6. Let's say the initial velocity is -5. Oh, and let's clear everything. Oh, not -55. Let's say -5. And let's say this is +2. When we run this, it's a variation on this one. Ooh. So again, this guy's going to smash into that wall. And this time, there's going to be a large negative acceleration, right? So again, we see right here, when he hits the wall, the slope is large and negative. That's why we see a large negative acceleration down here. Notice at this point, velocity is 0. Notice right here, the slope is 0. So the VT graph actually goes both ways. It relates to acceleration and the position. So this one, we could see that all these things are interrelated, and you have to know all of them. Look at this. There's an area right here that I'm trying to draw. Does anyone remember how that area relates to anything? What is this area related to?
Amount of distance traveled, right?
It is. I would want to be very careful. I'm going to call this A1. I would call that displacement or change. Obviously, that does relate to distance as well. Nice job, Alonzo. So, oh crap, I just about wrote displacement. It's the displacement. It's the change. So notice the change from right here to right here is equal to that area. So this is equal to area 1. Now, if you look at this, you could do 1/2 base times height to get that area. That area would have units of area of the base, which is in seconds. And over here, the height is in meters per second. Base times height would have units of meters. So that's going to give you some amount of meters. And because it's an area below the curve, this area should be a negative value. It has a negative height, right? The height was -6 initially. So that's how the areas relate. Okay, now over here, this area would be positive. And so notice on this part of the graph with this positive area, that's why we get a positive displacement. We'll call this area 2. That's the displacement in the second half. So that's a positive displacement. And then going to Alonzo's question, the distance traveled would be take the absolute value of those two displacements and add them together. All right. Whew. Let me get out of here. All right, questions. Is some of this make it? I'm trying to give you a feeling for it. We should probably look at some questions and look at the details now. Let's do that. Let me get me on speaker view and let's go to here. Let's see what I got here. Let's go to this problem. Okay. So if you want to, this problem kind of walks you through stuff. Remember, some of the problems you don't have to write out. It's just read through them, follow the solutions, make sure you can follow along. I think this is one of them. And it goes through all the stuff that we've just been doing with a worked example. Here's another one that's pretty good. You could see in this case, there's multiple acceleration stages. And again, the first thing with any problem is make sure you recognize the type of plot. Then once you recognize the type of plot, go to your workbook and on page 31, make sure you grab the right set of rules when you're going to play with it and learn about it. So make sure you grab the right set of rules. Once you have the right set of rules sitting in front of you, you can hopefully do the tricks here. And again, this one you could do there. I want to get to this problem. All right. So let's say we want to look at this problem. Okay. We have a plot of position versus time for an evil alien named Zykra. We will assume to the right is the positive. So again, I hat is to the right. All right. So in this case, let's try and talk about what this question means. I'm less interested in the answer right now than how we might attack this thing. And I think if I go down just a little bit, I think if I go to 180, I might be able to get the whole thing on here. Oh, whoops. There we go. So now I've got the whole question up there. What is this question asking us to do? What is part A asking us to do?
To identify when velocity is positive.
Yeah, so when is v greater than 0? How do I get velocity for this type of plot? Well, let's look. What type of plot is it? An xt. How do you get velocity?
Meter over second. So the slope.
Slope. So we want the slope. When is the slope positive, right? That's what we're asking here. If we want a positive slope, well, I could see that right here. Here's a positive slope. Everywhere between those two lines, right here and right here, that's a positive slope. Similarly, right between here and here. Got it. So what we've done is we've translated, real life motion into meaning on a graph. Cool. All right. How about this part B? It says estimate Zykra's velocity at 4 seconds. How would we do that?
The slope at 4 seconds.
Do the slope at 4 seconds. Now, to save us some time, I'm going to show you something interesting here. I've got it up here, I think, 2.28. Remember, if you want to find a question here, you hit, what is it? Control F for find, and then what 2.28 should pop you right there. Whoa. Okay, so let's scroll down. Now, I just want to show you here. Sorry, Jesse. Red and green. My bad. Okay. So now in this case, there's a slope right here. And then there's a big slope drawn right here. I'm going to do that with a dashed line. Okay. The idea here is the big line gives the wrong slope. Very obviously, if you look at it. I discovered this when I gave this on a test. A lot of students try to use the big red line, or basically this dashed line right here that I'm trying to draw. Okay. A lot of people try to use that dashed line, which is totally wrong. I think it's off by more than 40% if you look up here. The key is try to pick 2 points on a grid line that are close. So here what I did is I lined these points up on the time axis. That's great. You could have also lined them up here, or sorry, on the, you could have also lined them up on the x-axis. But basically make sure the points line up on some grid lines, and then pick points close to the time interval of interest, and you'll get an accurate number. So these are this shows you, again, these red points incorrectly estimate this, and you get a 40% error. That's terrible. So you would lose points. All right. So anyways, here's the actual calculation that I did using these points here, these other points, these green points. And just to make sure. So I just want to make sure you use these 2 points right there, and that's how you can get the slope as a good estimate. All right. Let's go back to the sorry, wrong button. Come on, Zoom. I meant to click this button. Sorry about that. All right. And so you could do all this stuff now, I think. Let's look down here at the next problem. What's the first thing I'm going to ask you to look at?
What type of graph it is?
Boom, you got it. So make sure you look at the right type of graph. Make sure you get the right set of rules. So we got a VT plot now. All right. So now, how about this question? We're looking for instance Vega is at rest. Are there any?
Yeah.
When?
2.
At 2 seconds right here. Remember, in this one, velocity is not the slope. It's just the value. So at rest means V equals 0. On a VT plot, that just means where does it cross the axis? Right there. And I think there's another one right there. Nice job. All right. How do we get Vega's acceleration at 2 seconds?
Slope at 2.
The slope at 2. Now look at this one. This one, you could actually use this point here and that point here. Why is that okay? Because it's the same slope throughout the entire interval. So people are used to getting the slope of a straight line, and then you could use points far away, and that's actually a great technique. But for that upper one where things were changing, just trying to get them both on here at the same time, right? There's a big difference between figuring out velocity on the upper plot. You have to get a slope and pick points close to the point of interest, versus on this lower one, you could just pick the values of V, right? If you want to get acceleration, you can get a slope, and because it's linear, the same slope everywhere will give you the acceleration between 0 and 4. And then again, you have the same slope everywhere between 4 and 6. So those are the kinds of tricks you got to look out for. And then let's look at this one. How about distance and displacement? If we're doing, let me get back into here. Let's do 200 again. Again, we got a VT plot. How do you get the displacement between 4 and 6 seconds? How do you do that? Do you remember?
Area under the curve.
Area under the curve. So in this case, I'm going to do something. I want you to watch carefully what I do, and then you can castigate me later. I'm just going to get the area of this triangle here. Will that be the area under the curve?
No.
No. Students do this all the time, and it makes me want to strangle a dead cat. So this is not the area under the curve. Bad. Bad, Rob. You got to watch out, right? This, all your areas are drawn to that line. So you have to get this area, which is positive, this area, which is negative, and then add them together. And so you'll get a partial cancellation. Go ahead. Question? Or, oh, okay, sorry. Any questions on that? So this is area 1. And remember, you've got the answers. You can look at these later. I'm just trying to give you the theory here, and then you got to check the details yourself. Area 2 is less than 0. So then displacement is going to be area 1 plus area 2. To be clear, distance, and I saw the chat, I'll get to there in just a second. Distance would be the absolute value of area 1 plus the absolute value of area 2. Remember when we did that problem earlier in the day with the calculus and we said, oh, it's moving this way, then back, then this way or something. And we said, first get this area, or first get this distance, then get that distance, and then get this distance. Anytime an object turns around or reverses direction, it gets complicated. And that's when you have to split things into chunks and get the distance that way. I'm going to pause there. Go ahead. Any questions, or I'll check the chat. Oh, cat got computer. Gotcha. Okay. Oh man, the cat was probably upset about me saying strangle a dead cat. Make sure you apologize for me. All right. All right. Let's see here. Okay. What do you think? Is any of this making any sense or questions?
It's crazy.
Sorry, what was that?
It's crazy.
Yeah, it's crazy. It's a lot of stuff. Again, you got to hang in there. Uh-oh. Yeah, well, that's cool. That cat, yeah, probably. Yeah. It's just like every student. Students want to strangle me too, right? Yeah, this is being recorded. So the live stream, if you need that link, Gustavo, somebody's probably got the link. If anybody has it, throw it out there in case Gustavo needs to look at it later. So yeah, right on. At least it says it's recording. Oh, thanks. Thanks, Jake. All right. So cool. Yeah, so there's so much. You could go back and watch the live streams later. I'm also live streaming my earlier lectures, which are pretty similar to these, but if you want a different take on it, to be honest, your lectures should usually be better than theirs, because I just did that and realized where I need to click, and I'm just a little faster in your lectures than theirs. So yeah, you guys got lucky. Yeah, you got lucky with online class. Yeah, whatever. Let's go back and look and see if there's something else I wanted to say. Oh, okay. We talked about that. Okay. And this stuff. Well, if you know the acceleration and you know the initial position and such, you could figure that out. Let's see. Did I mention this? Ooh. Do I know? Could I write the position as a function of time for this one? What do you think?
Yeah.
I say no. Not perfectly. Oh, wait, it says assume this. Oh, okay. Do not assume this graph is, oh yeah. What's the problem if we try to figure out the position? What piece of information did I not give you?
Initial position.
The initial position. So usually we would then assume the initial position is 0. So let's just check in 2.29 if we scroll down. Okay, so this shows you all this stuff. Blah, 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 blah. Oh, I think I forgot to answer it. Oh my gosh. I must have added some parts and forgot to answer them. So what is this? I'll have to add that in the solutions. Great, more work. What problem is this one? Sorry. 2.29 F and G, right? Okay, so I'll write that on my list of crap. Is it this paper? Yeah. Always more work. All right, listed. We'll get on it. Wait, I want, where's Zoom? Let me get back to here. There we go. There's the chat. Yeah, I just forgot to write F and G in there, so that's my fault. I probably had that written and then the scrap of paper got lost or something in the mix. Whatever. I'll get on that. Okay. What the heck? Let's talk about one last thing here. So we've kind of been working our way backwards. We talked about calculus. We talked about graphs, and there's all your graphs. So here are some examples of some word problems. You can see that's the last piece. My plan is to attack this on the next class day, but I will just mention here, just to kind of foreshadow it. Let me go back to the beginning. We're doing things in kind of a weird order here. I figure a lot of you had high school physics, and this might be where you're best at. The strategy for attacking these things is the following. We're going to read the problem, draw pictures of it. If you don't draw pictures, you're going to be in trouble. If you don't label your pictures, you're going to be in trouble. List the stuff you know or don't know, or list the things that you're assuming. List your equations, reread the problem, make sure you know what you're supposed to do, and then solve for things algebraically plug in numbers, and then check things like units, etc. Now, we could do a problem like this, but maybe what I'll do is I'll show you here. Somewhere I had these equations. Here are the equations if we have a single stage constant acceleration problem. If you're doing a constant acceleration problem, I just want to talk about these. This is a subset of all the calculus. Rather than doing calculus all the time, if you have constant acceleration, we don't need to use calculus to derive the equations of motion. You could use these or these. Now, before we get ahead of ourselves, let's just look briefly. Delta x can be split up this way, right? Delta x, you could put the initial over on the other side. Now, sometimes we're going to use these symbols, right? So sometimes we use delta x. Sometimes certain textbooks will say v final x. Others will just say vx, okay? Some books will say v initial in the x direction. Some will say velocity at time 0 in the x direction. I will use both of them, and I don't mean to mess with you. There's actually a fifth equation of motion here if you want. I don't know if you've noticed this, but this first one doesn't have v final in it. This next one doesn't have time in it. This next one doesn't have x in it. And this next one doesn't have a in it. So the last one would be an equation that doesn't have what variable?
Quick question. What
Oh,
page
go
is
ahead.
it, by the
Oh,
way?
sorry. I'm sorry. I forgot to say the page number. I'm a bad person there. My bad. Sorry about that. Let me tell you where that is. This is page 21. Sorry.
All right. Thank you.
Sorry about that. Yeah. Oh, man. Usually I remember to do that, but definitely anytime I do that, just blurt out. Sorry about that. So again, there's an equation with no v final, an equation with no time, an equation with no x, an equation with no a. What's the last equation we would write? Equation with no...
The initial.
Yeah. And so it looks a lot like, I believe it looks a lot like this one, except I think you get a minus sign here, and this is a v final, but you could check that out. Okay. But the fact remains is rather than doing calculus, if you have a constant acceleration problem, we're going to jump to these equations. Now, be careful. I'm going to show you something here. Remember, when I write that equation, there's an implied I hat. Okay. And so we usually cancel them out. So you are expected to know that delta x in this form means displacement. That's a vector, which could be plus or minus. It does not mean distance. Distance is always positive. Displacement, as we've seen today, could be positive. You could change position to the right, or you could change position to the left. It could be positive or negative. And if you need all these definitions and stuff and what things look like in various books, this is page 21. Sorry, I got the page number last. That's my fault. All right. And so if you want, because I'm sure you're all caught up on the homework, no way, right? But if you wanted to maybe look at some problems, you could look at some of these first ones. These are pretty easy. Again, I believe these ones are ones with numbers that you don't need to write out, but you could try to follow along with them and read carefully. And these are really good to basically worked example problems. You could view these as worked example problems. And this is a really fun one right here. We see, how do you handle a problem where the acceleration changes? So you do one problem for this, and then you do a different problem for this, and you use the constant acceleration equations for each stage. So if you want to look at this moving forwards, I think we still have, what, 10 minutes left? Maybe I'll show you the solution, and we'll talk about this one to foreshadow the next class. So the idea here is I want to look at, I guess this is the next page. So this was page 22. Just making sure. Oh, no, it's 23, page 23. Okay. And so we see here, she's accelerating from rest to a top speed and then finishing at constant speed. So in this case, we see the acceleration is positive. Over here, the acceleration is 0. And if you want to learn how to handle these kinds of tricky word problems we could take a look at what I did in the solution. So I'm going to do that right now. And we're going to do more of this next time. So if you're burned out, you could just stop and leave and just give up. All right. But if you want to, I'll try and show you here. What is this? 2.1 3/4. So you can see I went into pretty strong detail on these things. Oh, looks like I color coded it wrong there, but whatever, you get the idea. So what I did is I'm making a list of, well, number one, I draw a really nice picture and I label it with all these symbols and words. Next, I make a list of the things I know and don't know. And I go through this and make this list. And you're probably used to this procedure. Next, I write down equations. Okay. Going on, I plug in anything that's equal to 0. So there's a few things that are equal to 0 here. I'm going to plug in whatever is equal to 0. And okay, when I do that, that makes my equations slightly easier to work with. And then I rewrite them. And then I do all the work for stage 1. I do it algebraically. At the end, I plug in the numbers. I check the units. And then again, I do this work for stage 2. And so we can take problems that have multiple stages and figure out the total time. Hey, a new world record. All right. Oh man, I am burnt. I need to stop. So I'm going to go ahead and stop the live stream because I'm cashed out. So I'm going to answer questions now. And I